To introduce today's speaker, who is Bill Wootters, who I'm sure is very well known to everybody here for his very long list of very fundamental and seminal contributions to the whole subject. All those contributions, today he'll be speaking on the origin of complex numbers in quantum mechanics, which I guess has been a very long-standing interest too.
Thank you, Richard, and thank you for inviting me to speak here. The first thing I want to say is that I'm not going to answer the question posed in the title. I don't know the origin of complex probability amplitudes, but I want to raise the question and then talk about one particular approach to it that I and some collaborators have taken. Okay, and to get into the problem, I want to recall something very familiar, a simple quantum experiment. We have here a photon. Maybe this is coming from a laser, maybe a very weak laser, so we can talk about one photon at a time. It's hitting this 50-50 beam splitter, and then this is a regular mirror, another beam splitter, and two detectors. And if you ask anyone who doesn't know quantum mechanics, what's the probability of the photon landing here or landing here, any reasonable person will say the probability is 50-50, a half and a half, because it could go this way or this way, and then for each of those possibilities, there are two equal possibilities here. So you have four possible paths, two ways to get up here. Each one of those ways has probability 1/4, so it's probably 1/2 of landing there. And so you get, say, so this is a reasonable prediction for what's going to happen. Of course, that's not what happens. What actually happens is if you set it up just right, every time you do this, the photon will land here. And we have a way of explaining that in quantum mechanics, right? We say, we're still going to look at all the paths, but we'll add up probability amplitudes instead of adding up probabilities. So the probability amplitude of reflecting off this first beam splitter is I over √2. So for this path, there's another reflection, so there's another factor of I over √2. Multiply those together and you get negative 1/2. So that's the amplitude for that orange path. And then the red path doesn't pick up a factor of I. So it's 1 over √2 times another 1 over √2 is 1/2. And then you add up the two probability amplitudes and you get the total amplitude, which is 0, and the magnitude squared of 0 is 0, so that's the probability. And similarly, you can get the probability of this. Now each path picks up a factor of I. When they add together, you just get I. The magnitude squared of I is 1, so that's the probability. And so that's how we compute probabilities, and we get the correct answer. And this is very familiar to us. It's been around for a long time now. It's kind of second nature. Yeah, that's how you compute probabilities. But outside of the context of quantum mechanics, this would be a very bizarre way of computing any probability in the world. And so I think even though it's very familiar, it still is worth thinking about where the heck are these funny rules coming from? Is there some deeper explanation? So the first question I want to ask is, why do we have to work with these square roots of probability instead of just with ordinary probabilities the way we would normally do in, say, throwing coins or dice? And also, why are these square roots complex? So the strategy for the talk here is I will try to answer the first question, but my answer will make the second question worse. Okay, I'm going to give a tentative answer to the first question, but it's going to work very much against the second question. And then at the end, I'll to address the complex business, I'll talk about our particular approach, which asks, maybe the real amplitude theory is correct after all? And I'll explain what I mean by that. Okay, so to get into my answer to why you want to have square roots of probability, let's consider photon polarization. Here's a polarizing filter. Here's a photon that's just emerged from the filter. And suppose we want to measure its polarization. In classical physics, there would be a box that is a polarization measuring device, and the photon would go through it, and the device would say it's at 42 degrees. But of course, there is no such device in the real world. No such device exists. you can't simply measure the polarization of a photon. Rather, you can let it hit a polarizing beam splitter, and it has some probability of going this way or this way. And from those probabilities, so there it is going that way, after measuring many photons, you can estimate the probability of the vertical outcome, which is what you see here. And from the probability of the vertical outcome, you can estimate the angle or get some information about the angle of polarization. So that's the way quantum mechanics works. And the standard account of this is through this square root of probability business. So here's the polarization vector. This is the amplitude for vertical. And you square that amplitude to get the probability. So you get this familiar cosine squared of theta as the probability of getting the vertical outcome. Okay, this is going to be now a completely different answer to that same question, for that same curve, different explanation for the same cosine squared curve, through the question optimal information transfer, the problem of optimal information transfer. So here, I'm going to ask you to try, I hope you'll forgive me if I anthropomorphize the photon here. I enjoy doing this. Imagine you are the photon, and you've got this angle, theta, that you're trying to convey to someone at the other end. And you're sitting here knowing that you can't do it, because they're going to give you a binary choice. You can either say vertical or horizontal, okay? Those are your only choices. So what do you do if you're the photon in a situation like that? Well, you say to yourself, I'm going to act in such a way that if all other photons acted in just the way that I act, the information will be conveyed. And so it acts probabilistically. It says I'll have a probability of going vertical. And if all other photons do that, then someone here could eventually figure out what the angle is or get close to it. Right, the angle varies continuously. Measurement is discrete, only two possible outcomes. And so now I ask the question, is the strategy that the photon is actually adopting here the optimal strategy for conveying information? Why should it be? I'm not sure. I'm just supposing. Nature is often efficient. Maybe it's efficient here. In the past, in classical physics, the connection between the past and the future was perfect. If you knew the state at one moment, you could perfectly know the state at the next moment. Here, that's not possible. There's not a perfect connection when measurements are involved. And so the state here is not perfectly connected to the outcome. But maybe it's optimally connected. Maybe it's as efficient as possible. Let's just see if that works. So to get into that, I want to take us completely away from quantum mechanics and consider this communication puzzle. Has nothing to do with quantum mechanics particularly. So here's Alice. She's going to think of a number. It happens to be between 0 and pi over 2. It's kind of like an angle of polarization, but we're not really thinking of it that way. It's just a number. And she's trying to convey that number to Bob. And the way that she's going to do it is she's going to construct a coin. She has the ability to make coins with all sorts of any probability of heads that she chooses. So she can make a coin that lands heads 3/4 of the time if she wants. And so she encodes the number theta in the probability of heads of a coin that she constructs, and then she sends that coin to Bob. Okay, so there, she sends it to Bob, and then Bob will toss the coin, try to estimate the probability, and thereby learn about the angle, or not angle, the number theta that Alice is thinking of. So Bob will flip the coin, but in this iteration of the game, the coin self-destructs after one flip. Okay, so this is going to be very limited. He tries to toss the coin, self-destructs after one flip. So he's not going to get much information. But what is the best they can do is the question. And I should say, theta is going to be uniformly distributed between 0 and pi over 2. So both Alice and Bob know that Alice is going to choose at random a theta between 0 and pi over 2, uniform over that interval. Okay, so the goal is to find the optimal encoding, probability of heads as a function of the number theta. And our figure of merit is the mutual information. We're going to take that as our mutual information between the number of heads that Bob sees and Alice's number theta. Okay, so we can think of that. Here's mutual information. You can write it different ways. You could write it as, say, a differential entropy of theta, not conditioned on anything, minus the conditional entropy, the differential entropy of theta conditioned on the number of heads. And if you write it that way, it suggests the interpretation, the amount of information that Bob gains about theta once he sees the number of heads that he tosses. Or you could also write it this way, because it's symmetric, just the ordinary Shannon entropy of n minus the entropy of n conditioned on theta. And that's the way I've written it here. So here's the this p of n, probability of getting n heads if the number is theta. Just average that over all thetas, you get the probability of getting n heads. Let's take the entropy of that minus the average entropy once you know the value of theta of n. This average here is, we're integrating theta from 0 to pi over 2 and dividing by pi over 2. Because this is where we assume the uniform distribution. And the uniform distribution, that's absolutely crucial to assume this uniform distribution. So, so theta is distributed uniformly. And the question is, what's the optimal encoding? And here I claim is at least an optimal encoding. In the case where Bob only gets one flip, one toss of the coin, Alice should do something like this. Say if the number of theta is in the lower half of the interval, she'll send Bob a coin that only lands heads. And if it's in the upper half, she'll send a Bob a coin that only lands tails. So that way Bob will get exactly one bit of information, and that's the best that he could possibly get in one toss. And of course, it doesn't really have to be exactly like this. It could be just the opposite, or you could have a curve that goes back and forth, up and down, as long as you only use the probabilities 0 and 1, and you use them each with the same amount, with the same weight. Okay, now we're going to modify the problem. Now we have two flips. Bob gets two flips of the coin. Alice knows that Bob's going to get two flips of the coin. So the question is, what's the optimal encoding now? And here it is. Here is an optimal encoding. Okay, so if Alice, this is her number, she decides to construct a coin that has either 100% probability of heads, or probability 1/2 of heads, or probability of 0 of heads. She sends the coin to Bob. He tosses it. Most of the time, he actually gets to know pretty well what Alice's number is. In fact, if he tosses it twice and he gets one head and one tail, he knows that it's in this region. That's actually very good for him. Anyway, this optimizes the mutual information. And again, I could chop this graph up into any number of vertical slices and rearrange the slices, and it wouldn't change the mutual information. Oh, yes? What is that? You're wondering what the number is. I believe this is 15/34 of pi over 2. And this one is 4/34. I'm quite sure I'm remembering that correctly. Is that what it looks like?
The question is, why is that optimal?
It maximizes the mutual information. Yeah, it's not obvious. But you can actually grind through the algebra and do it. You can actually just do it. Just take the derivatives and set them equal to 0. That's what it is. But except the next one is going to go 25 flips, okay? 25 flips. So this is kind of like sending 25 photons. And the question is, what's the optimal encoding now? And here it is. Optimal encoding with 25 flips. I did not work this out on pencil and paper. This was by computer. Okay, so the result of a numerical calculation. This is the best thing Alice can do if she's trying to convey information to Bob by handing him a coin that he is going to toss 25 times. And she knows in advance he's going to toss it 25 times. Okay, so, and again, all that matters is it's not the curve that matters. What matters is what are the values of probability that you're using, and with what weight are you using them? How much of the time are you going to be using probability 1? How much of the time you're going to be using this probability, and so on. That's what matters. But the curve is kind of nice to look at.
Alice doesn't get to know Bob's answers, but
she doesn't know anything. She doesn't see his output.
she doesn't see his output.
She doesn't know. Yeah, she hands him the coin. That's the end of it. She's finished. She's finished. And then Bob tosses it 25 times.
And the coin itself doesn't have a memory.
Sorry?
The coin itself doesn't have a memory either. It doesn't remember.
No, it doesn't remember. No, there's no memory here. None. Yes.
But it's a fixed coin with a fixed probability, so I guess I'm not clear what that curve is.
They're fixed. It's not really a curve. Yeah.
Oh, I see. Given her number, that's what she chooses for the weight.
Given 25 tosses, she chooses these for the weights. She has no. If she's trying to do the best she can, she has no choice about which probabilities to use. She only uses 8 different probabilities, or 9, or whatever, however many there are there, and she uses them with specific frequencies. That is, specific probabilities. And so that's all determined by this maximization. Okay, you think now he's going to go to 100 tosses. I'm not. That's just too hard for my computer to do. This is the last finite number you're going to see here. So let's go to the infinite number of tosses. Okay, now in an infinite number of tosses, she can actually convey an infinite amount of information because Bob can narrow in on the arbitrarily small on the value of theta into an arbitrarily small, distribution over theta, narrow distribution over theta. So we can't just maximize the information. Let's maximize the information minus the log of the square root of the number of tosses, because the information is going to grow typically as the log of the square root of the number of tosses. So if we subtract that off, then we get something that's going to be bounded, and we'll take the maximum of that. So we're going to consider a particular encoding, a particular curve, p of theta, p heads of theta, and ask, what kind of curve maximizes this in the limit? And the answer to that is the cosine squared curve. And you could see the finite curves were sort of looking like that. They were trying to go to a cosine squared. And this is what photons do. So this is my punchline here, that photons are, in this sense, doing their best to convey their angle of polarization through these probabilistic measurements. Now, I should say, this is not the only curve that achieves the maximum. Again, all that really matters is the distribution of probabilities that you're using. How frequently do you use each different probability? The curve determines that. Remember that theta is uniformly weighted a priori. So if you want to know what's the weight assigned to a particular probability interval here, you just go across to the curve and go down and see what's the size of that theta interval that corresponds to that, and that gives you a particular weighting function on this interval of probabilities. And that's all that matters. This curve happens to instantiate that, but other curves do as well. But still, it's a kind of a cool thing. Now, why does this work? What's so special about the cosine squared curve? The intuition is this. When you toss the coin, you've got this binomial distribution of heads and tails, and the standard deviation of the frequency of occurrence of heads is given by this formula, where p is the probability of heads, and capital N is the number of tosses. And you see that depends on p, so that if the probability is about 1/2, that's when you get the largest deviation. When the probability is closer to 1 or 0, you have a smaller deviation. The cosine squared curve has the neat property that it evens those differences out. Right here where the uncertainty is small, the slope is also small. And so when you look at what kind of uncertainty in theta you have, it's the same size as over here. So that's what's special about the cosine squared curve. Okay, or another way of saying that same thing So here I've just taken the derivative of cosine squared. It has the same form as the thing from the binomial distribution. Another way of seeing the same thing is here are the probabilities, say, of heads and tails. These are the possible pairs of probabilities. And if you picture the same delta of the frequency of occurrence of heads, just picture it on the probability interval. In the middle, it's big. Towards the ends, it's smaller. But if you simply reparameterize the pairs of probabilities on this graph, with the axes being the square roots of the probability, so the possible pairs of probabilities are just on this circle here, then these things come out to be the same size. So that's another way of seeing what's magic about the cosine squared, or also what's magic about taking square roots of probability. Now this is very well known in the statistics community, and I'll show you an example shortly. Yeah, Charlie.
So I know that if I'm trying to use a polarimeter, the easiest way to do it is to adjust the angle until I get the null. And
That's right.
And is that because my eye isn't doing it as well as a photon counter? Or is the photon counter still better at finding the angle by looking at the zero than by looking at the maximum or the equal in the two arms of the...
If you just do the counting,
any angle is just as good.
any angle is just as good as any other angle.
So in other words, your eye, this is the problem with my eye, not the problem
That is
with
true.
photons.
That's true.
I've been
As a matter
blaming
of,
the photons. Yeah, I should have blamed my eyes. Okay.
it's your eye.
Yeah.
Because any angle is just as good as any other angle. That's a remarkable thing. It didn't have to be that way, but it's true. You just choose it, fix it at a particular angle. You'll get as much information just leaving it there and counting as by doing any kind of sort of sneaky adaptive stuff. Okay.
Although, sorry, presumably that's only true if the prior distribution on the angles is uniform.
I'm sorry. Say it again.
That's, I guess, only true if the distribution on Alice's angles is uniform.
Yes, it's crucial.
Yeah.
It's crucial that the distribution on Alice's angle is uniform. And I think you're anticipating a difficulty. Yes, it's coming up. Okay, so here's my story so far. It's a great story, a wonderful story. So in quantum theory, it's impossible to have perfect correspondence between past and future because you have probabilistic measurements. You can't tell what the past was from the future. But as we've just seen, the correspondence is as close as possible given the limitations of a probabilistic theory with discrete outcomes. And maybe this begins to explain why we have to use square roots of probability, because these square roots of probability come out naturally in this kind of problem. Unfortunately, the story is not true. Why not? Because probability amplitudes are complex. They're not real. And so why is that a problem? Well, okay, so I think this is exactly what you were anticipating. The linear polarizations are, on the block sphere, are this great circle here. Okay, and I was assuming a uniform distribution over that circle. But that's simply not a natural distribution at all when you consider the whole block sphere. The set of all pure polarization states are represented by the surface of the sphere. If you perform an orthogonal measurement, like, say, vertical versus horizontal, then you can learn something about it, but you completely miss the phase. That's one thing. But that's not the main issue. The main issue is that, so the probability of vertical is cosine squared of gamma over 2, where gamma is this angle from the North Pole. The problem is gamma is not uniformly distributed, okay? Cosine of gamma is uniformly distributed between -1 and +1. But gamma is not uniformly distributed. Therefore, the information is not maximized in this sense, okay? So what we've done simply doesn't work. Yeah, Charlie?
Does this mean that even if you had a photon counter, if you had something that adjusts both the phase and that you would be better looking for the null rather than looking for a maximum?
That may, I think you want to not look for a null, but look for a place where the derivative is the sharpest, right? Where the probability changes the fastest. Right? I mean, that is, isn't that what you want? You want to look. You want to see where you're trying to discriminate something from something that's very close to it. But if you're at a null, if you move a little bit from that, it's still pretty darn close to null because it's a second order effect there. The probability depends.
But if I'm expecting no photons at all, let's discuss this after.
Yeah, okay, we can discuss it later.
Because this is a practical problem when people are trying to measure polarizations either with their eyes or with a photon counter.
And my first thought is you want to look for the steepest slope.
Steepest slope.
Because that's where you'll get the finest discrimination.
So that would mean that you would do something like wiggle the polarization and look for the greatest AC signal between the two orthogonal polarizations.
Yeah, but then you also have to worry about this about the statistics of the binomial distribution and how that figures into. So we'll have to think about it. Anyway, the fact is it doesn't work for the complex case. Okay, let's go on. Okay, forget that it doesn't work for the complex case. Let's keep trying to tell my good story. Okay, let's go to higher dimensions. Okay, if you go to higher dimensions, basically it still works as long as you stick to real amplitudes. So here you have a state vector. It gets mapped into a probability distribution. And again, you can ask the same question, okay? And again, what really matters is the a priori measure on this probability simplex. That's what matters. If you choose the right measure, then you'll optimize the information transfer in the limit of a large number of trials. And the real vector space theory, it turns out, does give you precisely the correct optimal measure on the probability simplex. The complex theory gives you a different measure. It's not correct. And again, here's another way of picturing sort of what's special about these square roots of probability. If you go, this is another example of what I was showing earlier. If you parameterize probabilities by their square roots, so that the probability simplex becomes this piece of a sphere, then if you look at kind of the regions of uncertainty, the statistical fluctuations around any given point, they come out to be little circles all the same size, instead of being different shapes and sizes as they are in this flat probability simplex. And people have known this for a long time, and you see, this is a paper from Journal of Human Genetics, where they found it convenient to use square roots of probability just precisely for that reason. So square roots of probability would come out kind of naturally from that point of view if we were dealing with real amplitudes. But with complex amplitudes, it's just not working. One indication that it's not a very good match is that in regular quantum mechanics, in d dimensions, it takes 2 times d minus 1 real parameters to specify a pure state. Okay, so 2d and then minus 1 for the normalization, minus another one for the phase, overall phase. And then, but you only get d minus 1 independent probabilities from a complete orthogonal measurement. So there's this factor of 2 wrong. Yeah, yes?
Actually, I was wondering about this. So somehow there seems to be a kind of asymmetry between the choice of the uniform measure of the block sphere and Bob's measurement, because Bob's measurement isn't even complete to determine where the photon is on that. So if you give him an informationally complete measurement.
Oh, you can give him an incomplete. You can give him a complete informationally complete measurement. That's true.
Then would, for example,
then would it be? Oh, yeah. That's a great question. So, for example, suppose he makes a 4-outcome measurement of this tetrahedral measurement on the block sphere. Then at least he gets the full information, but it's not optimal in any sense. Okay. Because, no, or at least not in the sense that I'm talking about. Because if you think about, so the probability simplex there is a 3-dimensional thing. And if you were going to design a communication strategy, a probabilistic communication strategy that you want to make optimal, you would at least make use of the full probability simplex. Use all of the probabilities available to you. But the complete, that particular measurement never has a probability that gets larger than 1/2. So there are a lot of the probability simplex you're not using. So for my kind of problem, it's not optimal. Yeah, I was hoping that would work, but it didn't. Yeah. But I think that this business of why complex numbers, why complex amplitudes, is somehow related to this factor of 2, which I don't think we really very well understand that factor of 2. It's a pretty fundamental fact about quantum mechanics that it takes twice as many real parameters to specify a pure state as you have independent probabilities in a complete orthogonal measurement. But so somehow the complex numbers have to do with that. Well, people have certainly posed answers to the question, why complex amplitudes? You could say because we want some property of our physical theory. For example, Stueckelberg said you want to have an uncertainty principle of a certain form. He tried doing it with real numbers. It didn't work, so he had to complexify his theory to make an uncertainty principle. Lati and Machinsky also did something all along those lines. Many people like the idea of local tomography, that if you have a system consisting of parts, can you distinguish any two states of the whole simply by making measurements on the parts and paying attention to the correlations between the outcomes of the measurements? That's true in quantum mechanics, but it's not true in the real amplitude version of quantum mechanics. And so
if you had real quantum mechanics, you would have a kind of information locking. You could hide information.
yeah, that's true. You could hide information.
Bipartite correlation.
Yeah.
You could never get out
That's right.
infinitely many copies of the thing.
That's correct. That's right. That's right. There's a certain state of a pair, and people could be looking at the individual elements of the pair and never ever see this particular funny correlation that the pair embodies. Frankly, I could live in a world like that. You know, that wouldn't bother me too much. So I mean, I don't think the world. I don't see why nature would have to satisfy this. I could live in a world without an uncertainty principle of a particular form. I mean, okay. So Goyle and others have said you want complementarity, true complementarity. In effect, what they're doing is they're enforcing that factor of 2. They're saying we insist that there be a factor of 2. That's fundamental, important in physics, that there be a whole different set of degrees of freedom represented by the phases. Or you could say, I just want every transformation to have a square root. Scott Aronson has mentioned that in a little paper. And then many people you ask will say, yeah, of course it's going to be the complex numbers because they're algebraically closed, and that's an elegant property. So there are ideas out there. One of those might be it. One of those might be actually nature's true reason for using complex numbers.
How do you distinguish nature's true reason from the false reasons?
Was what?
How do you distinguish nature's true reasons from her false reasons?
Yeah, no, you have to have a deeper theory. You have to have a deeper theory, and then you have to, and how do you know it's a deeper theory? Well, because somehow it integrates parts of physics that were not integrated before. And then you see, okay, within the context of this deeper theory, we see, oh yes, it was local tomography. We see where local tomography comes from now. I mean, that could be, you know. Okay, but a different approach, an approach that kind of I and my collaborators are taking it. Well, maybe forget about this factor of 2. Maybe the real amplitude theory is correct. Okay, can we just adopt that assumption and see where it takes us? Okay, the real amplitude theory is just correct in spite of all of the evidence against it. Okay, well, this was kind of done by Ernst Stueckelberg. This is Stueckelberg. In the 1960s, he and collaborators wrote a series of papers called Quantum Mechanics in a Real Hilbert Space. And he wasn't talking about some hypothetical alternative theory. He was talking about actual quantum mechanics, but just expressed in a real Hilbert space. So he didn't deviate at all from ordinary quantum theory, just wrote it in a different way. And it's clear you can do this. Basically, you double the dimension. Suppose you have a d-dimensional complex theory. You double the dimension. You have a 2D dimensional theory and make it real. But if you simply do that, you get too much, okay? You get, and you say the orthogonal transformations are the allowed evolutions. But there are too many orthogonal transformations in a 2D dimensional space, way more than unitary transformations in a d-dimensional space. So you have too many possibilities. You have too many states, too many transformations. So Stueckelberg required that every operator in this bigger space commute with this particular operator, where J is this 2 by 2 matrix and I is the identity, say D by D identity. Or he was typically in an infinite dimensional space, so he didn't have to double the dimension. It was already infinity. But everything had to commute with this. And it's clear you can do that. Just notice that every operator that commutes with that, or every 2 by 2 matrix that commutes with that 2 by 2 matrix is of this form. Okay, A's down the diagonal, B here, and minus B there. And if you just take matrices of that form and multiply them together, it's as if you're multiplying complex numbers together. And that's the real part, and this is the imaginary part. So you can imitate complex numbers by imposing this requirement on everything. Okay, so we don't want to do that. We don't want to impose any requirement. We're just going to see if that requirement can sort of come out automatically, dynamically. Okay, so we start with a real amplitude quantum theory, and this work was done with Antonia Alexandrova and Victoria Borsch. Antonia is a graduate student here at Cambridge, even as we speak, in physics. So this is our model is called the U-bit model. You'll see why. So what we assume real amplitude quantum theory. Everything that you would ordinarily describe, say, as a d-dimensional quantum system, say a qubit, okay, take a qubit with dimension 2, is now going to be described as a 2-dimensional real object. And a qubit will be described as a rebit, okay, real 2-dimensional object. That's true for everything in the world. And in addition, there is one special object in the universe, which is called the U-bit. It's also a rebit. It's a 2-dimensional real quantum system. And now here's where I'm asking you to swallow something. It can interact with everything in the world. Okay, it has no location. We don't know much about it. It's just out there, and it can interact with everything. That's why it's called the U-bit. It's the universal rebit. So our model then is you've got some local system that you're studying. It's interacting with the U-bit. But the U-bit is also interacting with everything else in the world, which is this huge environment. And our question is, what is the effective theory? What's the effective theory of this piece, okay, when you don't have access to the environment? What does it look like? That's what we look at. And basically, the punchline I'll give you right now is we can get an effective theory that's very similar to standard quantum theory. Okay. So why do this? I'm just really taken with the idea that doubling the dimension is only a matter of adding one little binary thing. You know, doubling the dimension is easy. You just add one little binary thing. That doubles the dimension for the whole universe. Okay. And that's all you need. So you only need one U-bit. You would think that if you have, say, 7 qubits, you might need 7 rebits, and then 7 U-bits to make them all into qubits. But no, you need 7 rebits and 1 U-bit to double the dimension and make them all into qubits. Okay, that's a neat thing. Yes, Adrian.
What if we do look at both the local system and the environment?
Oh.
Do we get an effective theory?
Oh, if we can see the environment, then we have a theory that's different from quantum theory. Then it's a different theory altogether. It's real amplitude quantum theory. So the underlying theory here is real amplitude quantum theory. So if you can see the whole environment, you can see that you're not living in a regular quantum world. But if you can't see the whole environment and you're only looking locally at your part, then it can look very much like an ordinary quantum world. Okay, let's keep going. So roughly, the U-bit is playing the role of the phase factor. Basically, we've taken the complex phase factor out of the theory, and we've stuck it back in as an object. Okay, it's now an entity. It's an object in its own right. You can sort of think of its 2-dimensional state space as being spanned by 1 and I, sort of the basis vectors. We do not use this picture in our analysis at all, except it's just kind of helpful for the intuition. That's what the U-bit, that's the role the U-bit is playing. Okay. So here's what we're actually doing. Here's our system. The dynamics is generated in real theory in real amplitude theory can't be by Hamiltonian. We don't have access to I. So the dynamics is an orthogonal transformation, just a rotation of the big vector space. It's generated by an antisymmetric operator S, which we call the Stuckelbergian, and in honor of Stuckelberg. And here is the equation of motion. Okay, and what is our S? How do we choose our S? It has 3 parts. This is the u-bit part here. So this first part here is simply causing the u-bit to rotate. The only internal dynamics the u-bit has is rotation. It's a little 2-dimensional real object. It can only rotate. And omega is the rate of rotation. It's the angular frequency of rotation of the u-bit. This next piece, that's the u-bit interacting with the environment. And S characterizes the strength of that coupling. And B is a matrix. It's got to be antisymmetric, and it's chosen at random. We just choose it. It's a random matrix here. And in our model, we do a lot of numerical stuff. And we just choose these things randomly. Okay, in this last part, this is the only part that the local observer has any control over. Local observer, and this is the interaction between the u-bit and the local system A. So that's between here and here. So we imagine a local observer can choose this however she pleases. Which means that she can manipulate the u-bit in principle. But it turns out that because of the strong interaction with the environment, she's essentially really has very little control over the u-bit itself. She can try, but it's just not going to work. Nothing's going to happen because it's dominated by the interaction with the environment in our model. Oh, yes?
Any interaction between the local system and the environment?
No, not in our model.
Mediated via the u-bit?
Well, we're just trying to model what we would normally think of as an isolated system. So this is a model of, suppose you had a really isolated, say, a trapped ion, and it's precessing, or trapped electron, or something, and its spin is precessing around the magnetic field. Something like that. We're trying to model something that's really completely isolated for simplicity. We could certainly also do that. We could certainly imagine an ordinary interaction with ordinary other matter. We could do that. But for simplicity, we're just trying to model an isolated system. Of course, it can't be truly isolated here because everything has to interact with the u-bit. So I think I've said everything here. So basically, our tools here are numerical analysis and perturbation theory. We do a lot of perturbation theory with this ratio: strength of interaction between u-bit and environment divided by rotation rate of the u-bit. That is our small parameter that we perturb in. Yes, Jonathan?
Did you say that the pure state will stay pure on the...
Pure? Sorry?
A pure state will stay pure on the local...
A pure state will stay pure. A pure state of the whole system will stay pure. No question about that, because the dynamics is an orthogonal transformation.
Okay, but
however,
the thing we think of as quantum...
A pure state of this part will not stay pure, because it's not an isolated system, because the u-bit interacts with the environment. Right. That's going to be important. Okay, so the first thing we did was to sort of separate out the local system, just to say, what's the effect of the u-bit interacting with the environment? What does that do? Now, we're interested in this subsystem over here, and if you write the density matrix, let me do it over here. You write the density matrix of the UA system. That will be made out of a few things. It'll have the identity tensor something or other. So identity on the u-bit tensor something on the A system plus J on the u-bit tensor something on the A system plus the Pauli X operator on the U system tensor something plus the Pauli Z operator tensor something. So the u-bit part, I mean, I, J, these 2x2 matrices, I, J, X, and Z, are our basis for the 2x2 matrices. So any state of the UA system can be written in terms of those. So that's what I'm imagining here. And what we want to know is what happens to each of these components as time goes on due to the interaction between the U-bit and the environment. Nothing happens to this part because the identity commutes with everything, but stuff happens to these other parts. And here's what happens. We find, well, let me start with this X. The X and Z part both do this kind of thing. You get this oscillation. By the way, the dots are numerical results. The line, the curve is from perturbation theory. So this is what you get. It oscillates, and it finally decays to 0. Okay, and this is really, really good from our perspective. And the Z does the same thing. It oscillates and finally decays to 0. It means that because in this expression, the only things that don't commute with J are Z and X. And so if those go away, we're back to Stuckelberg's everything has to commute with J. So we really like these things to go away so we can get sort of make contact with Stuckelberg's rule. Now, if it were just the Stuckelberg thing, this part would not be affected. But in our model, the J part is also diminished a bit. For the particular parameters we've chosen here, it got diminished by about 1%. Anyway, it can, how much it goes down depends on the values of our parameters. But it doesn't go to 0. So you still keep a J part and an I part, but you lose the part that doesn't commute with J. So what we're going to assume, so having seen this, we decided what we're going to assume is we'll assume rapid rotation of the U-bit and very strong interaction with the environment. In which case, what happens is that those assumptions simply speed up these processes. So we make these decays arbitrarily fast. And so at all times, you're losing the part, any part that might have been created that doesn't commute with J. Okay, so you have a chance of being more like ordinary quantum mechanics. Okay, okay, and I'm just going to give you the results of our, I'm not going to go through all the details. Here's what we assume. Just as I said, we assume that both S, which is the U-bit environment interaction strength, and the U-bit rotation rate omega, they both approach infinity with a fixed ratio. We also assume the environment has an infinite dimensional state space. Okay, in the numerics, it doesn't go to infinity, but we make it big. That means there are infinitely many random parameters in that interaction matrix. And here's what we find. Here are our results. First of all, we recover Stuckelberg's rule because of what I was saying, because of the decay of the parts that don't commute with J. Everything ends up commuting with J. Also, even though this is a crazy theory with a universal rebit that's everywhere and interacting with everything, the effective theory is a no signaling theory. So there's no signaling through the U-bit. If you have sort of, here's the U-bit, here's A, B, and this huge environment, you try to send a signal from A to B through the U-bit. It just doesn't work because I think it's because the environment just eats it up. And you don't, that's, I guess, not a very technical explanation, but you don't get signaling. So you get some nice properties, even though it's a crazy theory. We also find, at least in our one case that we've checked carefully, that as this ratio approaches 0, we seem to recover standard quantum theory with no deviations from standard quantum theory. I should say, we've really only looked carefully at one case, which is a precessing qubit. And that precessing qubit looks exactly like a regular precessing qubit when you take the limit as this thing goes to 0. But if you don't take that limit, then you get some effects that you can maybe see in the lab if this theory were correct. Or I should say, if this theory is correct, we will see in the lab. So the first effect you see is a retardation of the process. So here's this qubit precessing around. Okay, the way it looks in our theory is it just goes slower. Okay, I think I'll leave that. There's more to say about that, but I'm going to jump ahead to the next effect. So this is an ugly effect. flattening of the Bloch sphere. So here it is. Here's the qubit precessing around. But what you find, if you just look at the density matrix of the UA system, that it seems to be going around a flatter Bloch sphere. Like it loses purity when it gets to here. But then it gains it back again over here. And then it loses it and gains it back again. As if it's going around a Bloch ellipsoid rather than a Bloch sphere. It's not a huge effect, but there is there. However, we can make that effect go away by redefining the U-bit. Okay, so we have this trick to use part of the environment as part of the effective U-bit, and then you can actually recover the whole Bloch sphere. And the reason we can do that is precisely because even though the thing becomes a mixed state over here, it's entangled with the environment, but the part of the environment that it's entangled with, the information hasn't gone very far away because you can get it right back again immediately. And basically, for that reason, we can do this transformation that gets rid of this effect. So far, I'm claiming that there's really not much difference from standard quantum theory. But here's an effect that we cannot get rid of, which is decoherence. So as the thing precesses around, we find that it spirals in towards the axis around which it's precessing. Okay, and it doesn't matter what the axis is; it'll always precess. It'll always spiral into that axis. Here's our numerical results, and this curve is the result of perturbation theory, but it also has some quantities computed numerically. We can also do a kind of a crude approximation for those numerical things, and we get a pretty simple expression that isn't quite right, but it's close. And that analysis actually gives us a nice prediction. We can actually compare to experiment. We have what is the coherence time? The coherence time is the period of precession times this combination of our parameters. It's a third order effect in perturbation theory. So that's why it's the cube of that ratio. And then we looked around to see what experimental result puts the most severe constraint on our parameter. And we found one by Dave Wineland's group where they have an atomic transition in a trapped ion. This is an optical transition, so the frequency is something like 10 to the 15th per second. But they've got this atom, or this ion, in a coherent superposition of two different states, which remained coherent for something like 5 or 10 seconds, so for a long time. And that puts a constraint on our parameter. So if our theory is correct, this parameter has to be smaller than about 1/1,000,000th. And that's it. So we have this U-bit model. It predicts slight deviations from quantum mechanics. But as long as the parameter is small enough, you wouldn't notice that. Wouldn't notice the deviations. Okay, let me conclude. So here's kind of a summary. If probability amplitudes were real, we could tell this nice story. Information is transferred optimally. And that maybe begins to explain square roots of probability. I still like that idea. It just doesn't work if the amplitudes are complex. Many ideas have been proposed to explain complex amplitudes, like this local tomography. But if you want to really stick to the real theory, no one can stop you from doing that. You just stick to the real theory. You can either do what Stueckelberg did and impose a restriction on all operators, or you can do what we've done, which is to assume this universal rebit. And in a certain limit, we do seem to recover standard quantum theory. But if you stop short of that limit, you get one particular effect, which is the spontaneous decoherence. Everything would decohere. But what may be more interesting is that this may be a way of generalizing quantum mechanics. That is, you start with the real vector space theory, but then look at the effective theory of a local system, and it's not quite the same as quantum mechanics. It's not easy to come up with generalizations of quantum mechanics, so this is possibly a way of doing that. You just have this big theory and look at an effective theory and see what it looks like. Okay, I think that's it. I'll stop there. Thanks very much.
Sorry,
Andreas?
This is a silly question, but are there ways of forcing quaternionic theory?
Oh, you want forced quaternionic theory?
Yeah, by putting kind of the right.
Well, you put in 2 U-bits.
Yeah.
You put in 2 U-bits. You start with the real theory. You start with the real theory. You put in 2 U-bits, and then if you insist that all operators of the theory commute with certain operators, you can do this, then it will automatically give you quaternionic quantum theory.
Can you go
Yeah.
beyond that?
Sorry?
Can you go further?
You can go further. What's it going to do? I don't know. Oh, well then, I don't know. Probably it gets very ugly. So you put in 3 U-bits. We know there's no quantum theory waiting to be discovered out there, I don't think, right? You put in 3 U-bits, and then you ask, what would be the rules? Well, you could just say there are no rules. You could just say, okay, put in 3 U-bits. The theory is what it is. Okay, it's some kind of theory, some kind of non-local theory. But to get rid of the non-locality, see, every time you throw in a U-bit, you've thrown in this universal, this potential for instantaneous signaling over arbitrary distance. So somehow you have to put in enough stuff in the theory to keep that from happening. So you put in a bunch of U-bits, but then make them rotate fast, make them interact strongly with everything, and maybe you can prevent signaling. Well, then what's the theory that comes out? Actually, that's an interesting question. In fact, the quaternionic question is, so you can get a quaternion theory in a kind of Stuckelbergian way by putting in 2 U-bits and then imposing commutation rules. But can you also get it by our way, which is you put in 2 U-bits and just let them interact strongly with stuff, and maybe that automatically imposes the right commutations, and you get the quaternionic theory. Jonathan, yeah.
So also the Stuckelberg rule, the commutation relations also is what stops signaling?
So the Stuckelberg rule what?
Is also what prevents signaling in...
Also, oh yeah, right, it prevents signaling.
Sorry.
Because it gives you standard quantum theory. You're back to standard quantum theory.
Is there a way of seeing why that commutation relation is what?
Yeah, why is that true? Another way of saying the Stuckelberg rule, actually Antonia did this in her thesis, that if you, but we haven't published this part yet, if you simply require that no information can be extracted from the U-bit, so that means 2 things. It means you can't measure the U-bit, okay? So it's unmeasurable. And then if you also say it can't interact with anything in such a way that by measuring this you would learn about the U-bit, then that's equivalent to Stuckelberg's rule, and you get back to quantum mechanics. So that would explain why you can't communicate with the U-bit, because you can't extract any information from it. So Alice could try to put some information in the U-bit, but Bob would not be able to get it out. Yeah, Beth.
Comment on Charlie's question and a question of my own. So in terms of if you could go beyond quaternions with 3 U-bits, I learned something at lunch. We were discussing this question at lunch. I'm not sure if you were there. And I sort of thought that the quaternions were the limit that you could do. And somebody told me there's something called the Cayley numbers, but you had to give up not only commutativity but associativity.
Oh yeah, the Cayley numbers. But I don't think anyone's constructed a Cayley number quantum mechanics.
Yeah, but that's why I was wondering if the 3 U-bit would have been.
Oh yeah. 3 U-bits with a Cayley number quantum, get a quantum mechanics. Yeah.
I had a much more elementary question, and that is, doing the real quantum theory is basically restricting to a plane of the Bloch sphere. I mean, all your pictures.
Yes, that's true. If you just do real,
And one of the things we know is if you look at the effect of noise in terms of completely positive maps, you can't map down to the whole plane. It has to shrink to an ellipsoid or a circle of radius 1/2. you can't get the whole,
You can't shrink all the way down.
you can't get a completely positive map that just collapses the block sphere
Down to the plane.
onto a plane.
Uh-huh.
It has to shrink it in as well.
Uh-huh.
And I'm wondering if what you're seeing, actually, well, you said it was,
I have a squished block sphere. Yeah.
Yeah, actually, I think you have to I'm not sure you can even retain pure states, but I was wondering if that was what was perhaps explaining this spiraling, because you're looking at noise is essentially the effect of the environment.
Yeah.
If the environment was enforcing this spiraling on you, was the same thing as saying that you can't just collapse to a plane and keep the pure state. You have to get something.
It may be related. It may be related. I mean, the way I think about the spiraling is, I figure, information is leaking out through the U-bit to the environment. So we've got an increase of entropy because of that.
Yeah, if you had that interpretation, then you ought to be able to have a theory that constrains your spiraling down to a radius of 1/2.
Oh, I see. Ours goes all the way down.
Yours goes all the way down.
Ours goes all the way down. Yeah.
Otherwise, you have to go down at least 2.
And then it bounces. Yes, Adrian.
So I was intrigued by the idea of generalizing quantum theory.
Yeah.
Am I right? It looks sort of inherently non-relativistic. I mean,
It looks terribly non-relativistic. It's terribly non-relativistic. That is, the full theory is outrageously non-relativistic because there's a universal time parameter here, time coordinate, and we have to be able to say what the U-bit is doing with this, how the U-bit is interacting with this particle over here at the same time that it's interacting with this particle over here. So it's only the effective theory that has any chance of respecting relativity. But even that, I mean, the whole theory is terribly non-relativistic. So I think it's conceivable. Maybe you can come up with some other version, a more sophisticated version of this theory, which may require a really different way of doing quantum mechanics, but that may be more compatible with relativity. But this version is not relativistic. Yeah.
And you don't have you're not hiding a relativistic version.
I'm not hiding one. No. But I don't know. I mean, I know people have worked on multi-time quantum mechanics, where you have different times for different particles. Each particle has its own time. It's not a very popular. I think not many people have done that kind of thing, but some people have. So I don't know. I just wonder if, there may be some way of reformulating quantum theory so that you can somehow get the U-bit and also get relativity. I haven't figured it out. I don't know. Yeah, Charlie.
Well, speaking of popularity, if you divided people according to whether they like standard quantum mechanics or the U-bit, and you also divided them between theists and atheists, would you get most of the population along the diagonal?
Oh, I see. Because there's something theistic about the U-bit.
Yeah, it's there, but you can't see it. And
it's universal.
It's all about you. But
Yeah. Right. Right, but it's only a rebit. That's kind of little. It's true. It's everywhere, but it's only a rebit. Yes.
So how does this spontaneous decoherence scale as you have more effective qubits?
Say that again.
So how does this? You have this spontaneous decoherence in the effect theory that might let you distinguish between this and standard quantum mechanics, experimentally, potentially.
How would you distinguish?
How does it scale, and does it, for example, would it rule out a threshold theorem?
Yeah. It's hard to distinguish this from ordinary decoherence. That's the question?
Yeah, but how does it scale as you add more effective qubits? Do you make your effective system larger? You're describing more than just one qubit.
Yes.
But more of them, because
Yeah.
I have no insight. But if it scales
How would the decoherence
fault
scale?
tolerance, they might be.
How would the decoherence scale? That's a great question. I don't know the answer to that question. I could try to guess.
Because maybe your theory is predicting the demise of quantum computing, because it's killing the threshold theorem of fault tolerance.
Yeah, I know. We don't want it, right.
It wouldn't be a nice story anymore.
Well, that would be something,
Wouldn't be
wouldn't
so
it?
unreasonable.
If
Can you be interactive?
we can't build a quantum computer because of the U-bit. I don't know the answer. It's a great question. I have to investigate. Yes, Charlie.
I think for that reason it might be very popular with somebody like Leonid Levin, who sort of leans in the anti-quantum computing and also the theological direction.
Oh, okay, I see. So the quantum computing deniers. Yeah.
Because God prevents it.
Right? See, the nice thing about our theory is we can keep turning this parameter farther and farther down as better and better quantum computers are built.
This thing precesses down
Yeah.
to radius 0
Yeah.
and then bounces back.
Oh, it just bounces a little bit. Yeah. No. When we do the perturbation theory, you get this kind of Bessel function of order 1, J sub 1. It determines the envelope for this thing. So it actually an absolute value of it. And so every time it hits a 0 of the Bessel function, you get down to the center. But then it pops up again. But it always gets smaller and smaller. I mean, it's decaying. The bounces. It's funny. Yeah, that's just what it does. That's what the numerics do, and that's also what our theory does. It has this bounce.
Think that
It is kind of funny.
the energy and
Oh yeah. Yeah. I mean,
and then suddenly
well, it's somehow. I assume what's happening is it's getting entangled with the environment in some way, and so the local system looks like it's completely decoherent. But then some of that information is coming back. I don't know. Yeah, something like that. Briefly, and then it goes away again. Of course, this is all our model. You know, you could change the model in many ways. We can change the model in many ways. In fact, I recently figured out that a lot of what we assume, our results depend on what we assume about the environment. We start the environment in a completely mixed state. Okay, that's a very hot environment. We could start it in a thermal state that's much cooler and more realistic, and get a different decoherence time, different coherence time. So a lot of probably the bouncing and maybe an artifact of our particular assumptions. There are variations on this model, is what I'm saying. Yes?
If you somehow elevated this optimal information transfer
Yeah.
guiding principle and use your modified U-bit sort of theory, does that contradict anything that we know experimentally?
Oh,
How robust is it?
you mean this?
Yeah, if you now apply that optimal information transfer to your, not to the, I mean, to this modified, to this enhanced system with a real.
Right.
With this U-bit.
Optimal information. So where does optimal information transfer fit into this thing?
Does it always work?
Well, optimal information transfer, it's the way we've formulated it, always works for real vector space quantum theory as long as you're allowed to make a complete orthogonal measurement, and as long as you're talking about pure states. Okay, so you're talking about Alice is sending a pure state to Bob. Bob is making a complete orthogonal measurement, and also you have an infinite number of copies or arbitrarily large number of copies. Then it's going to work. You'll notice that I didn't say anything about the optimal information transfer once I got into the U-bit model. And the reason is this optimal information transfer works only if you can actually make a complete orthogonal measurement on the whole system. And our local observer is not going to be able to make a complete orthogonal measurement even on her system and the U-bit because of the U-bit's interaction with everything else. So even though that optimal information transfer was kind of a motivation for real vector space quantum theory, real amplitude quantum theory, in the U-bit model, it's not very applicable because no one can actually do that. You can't do that measurement. So, but in a way, I guess that explains why we don't actually have optimal information transfer in our world. It's because we're limited on what we can do with the U-bit. And if we could measure the U-bit properly, we'd be able to do that. So I guess that's okay. That's a consistent story. Yes, Charlie.
That reminds me of the medieval, or the story about the medieval argument about the proof that the circle is the most perfect shape, and the reason that it's true is that my reasoning is circular and therefore it's perfect.
I'm not so sure. I'm glad that my talk reminded you of that.
Well, I guess we all have a lot to think about. Thank Phil for a very
Sure.